Angular momentum is the rotational equivalent for linear momentum. And just like linear momentum is P equals mv, this is L is the symbol for angular momentum. I is rotational inertia, right? The rotational equivalent of mass. And this is the rotational equivalent of velocity. It's angular velocity. So you get I omega is angular momentum. So anything that's rotating, right, has an angular momentum depending on its shape and how fast it's rotating. The law of conservation of angular momentum has the same exact structure as the law of conservation of linear momentum, right? The net initial momentum equals the net final momentum. So what that says is the total angular momentum must remain constant throughout an object's motion as long as there's no net external torque, right, acting on the system. So, for example, when you have an ice skater who's skating and they have their arms out, they have a certain amount of rotational inertia because their arms are out, right? That's greater because they're expanded like this and they're spinning at some rate. When they bring their arms in, they're decreasing their inertia, their rotational inertia, so their velocity has to go up in order to keep the angular momentum constant. So this happens in many situations, and you're going to need to be able to just apply this conceptually in order to grasp this. We're not going to do any math with it, but you have to understand that when you look at this, when you have your initial inertia times your initial rotational velocity, that has to equal your final inertia times the final rotational velocity. So if this increases, this has to decrease in order to keep this value, the initial, constant. So they're in inverse relationship.